Okay, so welcome to Math355 Abstract Algebra. This is our last lecture of the semester, lecture 25. And what I want to do today is talk a little bit about where does everything go from here? What can we do with the various things? So since a lot of you haven't done real analysis, I thought actually I would spend a little bit of time just proving that the matrix exponential converges, just so you get a sense of why might you want to take a class like this? And the problem is there are so many things that seem reasonable that are not. And so I'll first show you why the matrix exponential converges, and then I'll give you an example of a double integral where you can't switch the orders of integration. Rather than doing a double integral, I'll do a double sum just because it's a little bit easier to write down. You can smear it out and make it continuous in an integral if you want. So let's talk about the matrix exponential. So we defined e to the x to be the sum n goes from 0 to infinity of x to the n. And then e to the matrix A would be the sum n goes from 0 to infinity a to the n, where let's say A is a big N by big N matrix. So it's a square matrix. And what should a to the 0 be? What matrix should a to the 0 be? It should be the identity. Just like the exponential starts off 1 plus x squared over 2 factorial, e to the a should start off identity plus. So how big is n factorial? And I love it. You can actually end a sentence with a factorial and a question mark in English now. Well, we've talked a little bit about this before, I think, right? We did the integral test. We took the log. We said the log of n factorial is equal to the sum k goes from 1 to n of the log of k. That's about the integral from 1 to n of log of t dt, which is t log t minus t. Evaluate this at 1 and n. And so when the dust settles, you get, with more work, that n factorial is approximately n to the n e to the minus n squared of 2 pi n. Oh, yes. Both of these should have over n factorial. Thank you. Which is why I'm spending the time right now talking about what is n factorial. So with some more work, we can do that. Trivially, n factorial is greater than or equal to n halves to the n halves. Just take the second half of the product and replace everything with n halves, the midpoint. And so this would basically show it grows very fast, grows faster than exponential. So this is enough to show that it's growing faster than not than only an exponential, but even any polynomial, which is slower. Since my growth is n halves to the n halves, it's growing faster than n to the 2,000, or n to the 3,000, n to the 5,000. It grows faster than any polynomial. It's also going faster than e to the n because the n over here is growing. So I don't actually need the full strength of how big is n factorial. And this is a really good insight in doing mathematics, is try to think, what do I actually need? I can prove that n factorial is about n to the n e to the minus n by just using Riemann sums. With more work, I can prove n to the n e to the minus n squared of 2 pi n. But I don't need that. I just need a really weak bound. And this is something you should really try to get into the habit of doing. What is the weakest thing I can do that will allow me to answer the question that's asked? And I just need some trivial growth. So let's look at how big are the entries of a to the n. Let m be the largest entry of a. Okay. Let B equal the matrix of all entries being m. So entries of a to the n in absolute value will be less than or equal to entries of b to the n in absolute value. So why is that true? So I take all the entries of A and I replace every entry of A with the maximum value. I'll say the absolute value of the largest entry of A. The reason that the entries of B to the n have to be larger than the entries of A to the n in absolute value is that I can't have any cancellation now. Let's just consider A having real entries. So some of the entries could be positive, some of the entries could be negative. When I start taking powers of A, I could have some cancellation. I'm replacing every entry in A with a positive number. Unless every entry of A is 0, in which case it's really not that hard to calculate, A to the n. The other thing is not all the entries of A might be equal to m. By inflating them, when I'm looking at the powers of the matrix, I'm only going to get things larger now. So is this enough detail that the entries of B in absolute value are larger than the entries of A? The entries of B squared are larger than the entries of A squared. We can't have cancellation by sign, and we've boosted the product. Well, the matrix B is equal to M times the matrix of all ones, right? So B squared would be M squared. So what would the matrix of all ones times itself be? The matrix of all. Well, think, not all ones. You've got all ones hitting all ones. What's the size of A and B? Nope. Big N by big N. So what would be the entries of B squared? It would be M squared times the matrix of all ones times the matrix of all ones. That's the matrix of all n's. So B squared is the matrix of all n's times M squared. Now let's look at B cubed. I now have an M cubed, and then I have the matrix of all n's times the matrix of all ones. What will I get? N squared. Do you see how this is going to be all n squareds? Because when I have all ones, I'm just going to add n squared plus n squared plus n squared n times. So in general, B to the n would be m to the n, and then the matrix of n to what power? So what power would I have for the n's? Yes, to the n minus, and to the n minus 1. So the maximum entry of A to the n in absolute value is going to be less than equal to m to the n to the n minus 1, which is 1 over n mn to the nth power. So grows like mn to the n, so sum converges as divide by n factorial, which is going to be greater than or equal to n halves to the n halves. This is a fixed number. Once little n is sufficiently large, think of mn, even if it's a Google, n can be a Google factorial, 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 squared, factorial, 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 squared. You're going to eventually have an incredibly small fraction. And then you're fine by comparison test. So this is just a quick sketch that it actually does converge, that the matrix elements are growing. They could be growing exponentially fast, but n factorial grows even faster. And it's going to grow so fast that this will converge. And now, if you look at it, when I look at e to the a, I'm going to have a big N by big N sum of matrix elements. And I just go component by component by component. For each component, everything is going to be fine. So this is some of the things you do in a class like real analysis, is you find ways to justify arguments like this. Then you might say, but of course everything like this is fine. Why do I need to spend time? Do you remember the Fubini theorem for multivariable calculus? The integral over x, the integral over y of f of xy dy dx equals the integral over y, integral over x, f of xy dx dy if f is nice. That you can switch the order of integrations. This was one of the big techniques in multivariable calculus. Yeah. This is a chance to essentially review the math you've done up till now in your curriculum. There's two main ideas in multivariable calculus: switch the order of integration and change variables. If I give you something in Cartesian coordinates and you're integrating over a sphere, what should you probably do? Yeah, convert to what? You integrate. You're integrating over a sphere. What should you convert to? Spherical coordinates, right? If you're integrating over a cylinder, what should you integrate over? Cylindrical coordinates. It's kind of hard to disguise what we're doing. If you're integrating over a circle, we don't say circular coordinates, we say polar coordinates. The language is a little tricky there. But for which f is this true? So let's consider the following double sum. So I'm going to give you a bunch of points. I'm not going to be able to draw all of them in the interest of time. But I'll start drawing a few. So this is going to be the point 0, 0. This will be 1, 0, 2, 0, 3, 0. This will be 0, 1. This will be 1, 1. This will be 2, 1. This will be 3, 1, and so on, okay? And I'm going to define my sequence AMN as follows. It's going to be plus 1 here, minus 1 here, and then 0 for the rest of eternity going up. In the next column, it's going to be, I'm going to shift, it's going to be 0, plus 1, minus 1, and then 0 for all eternity. For the next one, it's going to be 0, 0, plus 1, minus 1, and then 0 for all eternity. Then 0, 0, 0, plus 1, minus 1, and then 0 for all eternity. So let's compare the sum m goes from 0 to infinity, the sum n goes from 0 to infinity of AMN versus the sum n goes from 0 to infinity, and then the sum m goes from 0 to infinity of AMN. So in the first one, I fix an m, and then I let n vary. So if I fix an m, I'm saying which column I'm in, and then I sum over the column. What do I get as I sum over any column? 0. And so if I sum 0 infinitely often, what do I get? 0. But if I look at the other one, I first fix a row. What do I get if I sum over the first row? What do I get if I sum over any other row? 0. So the total sum is going to be 1. So these are not equal. This is the simplest example I know to show that you can't always switch integrals. Now this is discrete, but I could always spread this out. I could define this to be maybe like a pyramid that has height 1 over here and comes down. You could make it painful to do, but the idea is clear. Order matters. What you need typically is if the double integral of the absolute value of f dA is finite, can switch orders. Basically, infinity is a danger sign. Whenever you have affinity in play, you have to be careful. And the problem is if I look at the sum of the absolute values here, it's plus infinity. I have to be careful how I arrange things. So this is just a little bit motivation. If you haven't done real analysis yet, what would you do in a class like that? Why do we care about content like that? Things have to be done carefully. Your intuition can fail. I could give an entire week-long series of lectures on all the times our math intuition fails. Most of the time it's right, especially the further you go in mathematics and the better intuition you get. I also wanted to do this because I'm not going to prove all of the results on the applications of group theory to counting primes. And it is work to do the analysis. And I just want you to be aware of what has to be done. We have all of these nice compartmentalized courses. This is abstract algebra. This is linear algebra. This is real analysis. Right. And when you're doing math research, you go, oh, well, I'm actually doing math research in abstract algebra today. I can't use any result from here. No, you use all the results together. The more you know, the more you can do. And you can say, well, for this problem, which methods would be helpful to study this type of problem? All right, so we've talked about the Riemann zeta function before. I know because I looked at the slides from earlier in the semester and I saw that we had done this. I've got a couple of links over here that are interesting to read. The first is from a colleague of mine on the dispute between who should get credit for an elementary proof of the prime number theorem. So the prime number theorem counts how many primes are there up to x. And to first order, it's about x over log x. And for the longest time, people couldn't prove this. And eventually, in 1896, two different people came up with proofs of this. And their proofs used complex analysis. And this seemed like overkill to use complex analysis to count integers. And eventually, two opinions emerged. There's no way to prove this without using complex analysis. This is fundamentally a result of our complex numbers. And the second is that if you could find an elementary proof, boy, will that open up doors. It turns out both are false. There is an elementary proof, but it doesn't really give us anything better. It gives us worse results, but it's a miraculous achievement to be able to do the sieving and to do things elementary. For the most part, you see professors acting civilized towards each other. You don't see many math disputes or math fights. There's been a few situations in mathematics where there's questions over who should get credit. And because this is being recorded, I will leave it at that. And I will refer you to the first article if you want to see some interesting discussion about the history of how a big result was proved and how credit was assigned and determined. So it's very well written, very well researched, worth reading. The other one is an article on just what I'm going to be doing today, proving primes in arithmetic progression, putting in all the details that I'm not going to put in. So the Riemann zeta function is defined as the sum of 1 over n to the s. You can also generalize this and look at zeta functions over number fields. And so we've talked about ideals and principal ideals and whatnot. You can actually use those to define a more general number function, a more general zeta function than the Riemann zeta function. Rather than summing over integers, you can sum over ideals. So the stuff that we've used actually has a role to play in generalizations. It's a question of which quantities are worth studying. So I am studying the sum of 1 over n to the s. Rather than a 1, we could put other stuff here. And we'll talk about how to use group homomorphisms to put good things up there. So the stuff that we were doing earlier in the semester is going to come back now. Using the unique factorization of integers, the fundamental theorem of arithmetic, we can write this as a product over primes of 1 minus 1 over p to the s inverse. And this converges as long as the real part of s is greater than 1. You should recall that this is a p series, hopefully from calculus, where instead of writing p, we write s because we want to reserve p for prime. I think it's unfortunate that they call it as a p series in calculus, but there's no chance of that getting changed. Okay, so the proof, as I said, is the fundamental theorem of arithmetic. I'm just using the geometric series formula. And so we're using the fact over here and geometric series formula. And that's just going to be 1 plus x squared plus x cubed plus dot 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 equals 1 over 1 minus x if the absolute value of x is less than 1. And there's lots of fun ways to prove that. And so by using those two things, we can show that the sum is the same as the product. And the hope is that if we understand the sum, maybe we can use that to get some information about the product. So we talked last time that if we take s equals 1, this is the harmonic series which diverges. So that should imply that there's infinitely many primes. And so let's see that a little bit more carefully. So let's look at the log of zeta of s. That's going to be the log of the sum n goes from 1 to infinity of 1 over n to the s. And that's going to be the log of the product over primes of 1 minus 1 over p to the s inverse, at least if the real part of s is greater than 1. All right. Hopefully you remember your Taylor series. So Taylor, the log of 1 minus x. Does anybody remember the Taylor series? So this is going to be negative x minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4 dot dot dot. And what we're using is, the Taylor series of f at x is f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus dot dot dot. And you just have to take the derivatives. So the idea is, if x is really close to 0, then 1 minus x is close to 1, and the log of 1 minus x is going to be close to 0. How close? Well, we can expand it out. And the first order correction is of size negative x. Well, that makes sense. If x is a small positive number, the log of 1 minus x is a little bit less than 1, its log should be negative. So this is reasonable. If x is a negative number, 1 plus x is a little bit greater than 1, its log should be a small positive number. Always do quick sanity checks. All right, well, what's the log of a product? What will some of the logs? So we have the log of the sum n goes from 1 to infinity of 1 over n to the s is equal to the sum over the primes of the log of 1 minus 1 over p to the s inverse. Well, I can pull out the negative 1, right? And I'll have the log of 1 minus 1 over p to the s. And now what I'm going to do is I'm going to expand that using Taylor series. So this is going to be this negative sum over p. The first order term is negative 1 over p to the s. The next term is minus 1/2 1 over p to the 2s minus dot 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 dot. Okay, well, the negative signs all cancel. So we get the log of the sum n goes from 1 to infinity of 1 over n to the s is equal to the sum over p of 1 over p to the s plus, I'm going to just say good in the interest of time. I'm going to resist the fact that I want to do analysis and not. What goes on over here? I'm going to have p to the 2s. So if the real part of s is greater than 2, greater than 1/2, if real part of s is greater than 1/2, then the sum of 1 over p to the 2s, what can you tell me about the exponent? This is clearly going to be less than or equal to the sum of 1 over m to the 2s, right? Instead of summing over the prime, sum over all the integers. But this is a p series with p greater than 1. So it converges. So do you agree that as long as the real part of s is just greater than 1/2, the sum of 1 over p to the 2s is going to be fine? And then the next one is going to be 1 over p to the 3s. That's going to be fine. And you can show that even though I have infinitely many of them, it's going to be okay. One way you could do it is you could say, look at all the evens, and all the even with all the powers would be dominated by this. And all the odds would be less than this. So as a nice exercise, you could say, or even powers a subset of 1 over m to the 2s, odd powers greater than or equal to 3, half or smaller of this. So really, I could dominate all of the stuff from here onward by just twice this sum. And I even have a factor of 1/2, 1/3, 1/4. I don't even need the factor of 2. I'm trying to just give you a sense of what do you do with an analysis class? How do you handle stuff like this? This stuff is going to be a finite number. So all of this leads to, this is going to be finite. So if I take the limit as s goes through 1, this is going to explode. So this has to explode. So there must be infinitely many primes. I'm going to do something a little bit okay. So let's truncate some at, say, x. And then it will take s equals 1. And we'll truncate the product at x. It's not fair to do that. But I'm just trying to give you a rough intuition. This is for intuition. So then the intuition would be the log of the sum n less than equal to x of 1 over n is like the sum p less than equal to x of 1 over p plus something finite. This is the nth harmonic number. The sum of the reciprocals of the integers up to x is about the natural log of x. So this side is approximately log x. And so this is saying that not only are there infinitely many primes, but there's so many that the sum of the reciprocals diverges. And if you sum the primes up to x, it's about log x. This is true. I have not proven this rigorously. I've just said, hey, what if I just truncate this sum and truncate this sum instead of, that's why we need classes like real analysis to allow me to do that. But no matter what, at this point, we already see enough to show that there's infinitely many primes. Because as s goes to 1, this blows up, so this must blow up. This is to get a little bit more. Not only does it blow up, but it blows up at such a rate that the sum of the reciprocals of primes is about log x. So again, all I want you to get from today is a sense of what's out there, what can be done next. With more analysis, we can get a sense of how many primes there are. If you looked at the sum of the reciprocals of the squares, that would converge. 1 plus 1/4 plus 1/9 plus 1/16. This is a p series where p equals 2. There's a lot more primes than squares. Probably the most famous of the infinitude of primes is Euclid, or at least I'll say Euclid's proof. I'm not sure if this is due to Euclid, but it's definitely popularized in his book. If only finitely many primes say P1, P2, ... Pn, consider P1, P2, P3, ... Pn plus 1. If prime found a prime not on our list. If composite must be divisible by a prime, but P1, P2, ... leave what remainder when you divide by them? So if I divide this number by P1, what's the remainder? So if I divide x by P1, x is the product of the primes plus 1, what would be the remainder? Nope. Nope. 1. The remainder is 1. If I divide by P2, what's the remainder? 1. But all of these leave a remainder 1. So divisible by a prime not on our list. So this is a proof that there's infinitely many primes. With work, I'll make this extra credit, show at least some constant times log x primes up to x by this. So if you consider the worst possible case where you have to take all the primes and add one, and that's your next prime, show that this implies that there's at least log x primes up to some constant, up to x. The actual answer is of size x over log x, much bigger than this. This is a horrible lower bound. This is like telling you, I spent some time this morning looking at the Wall Street Journal, watched CNBC, did some Googling. Elon Musk's net worth is at least $15. That's a horrible, horrible lower bound for his net worth. And I predict by the end of the year, it will increase to at least 20. Horrible. But it's a true statement. This is a true statement, but it is very far from the true bound. Now, we could consider progression. So what about primes in arithmetic progression? Say, P congruent to A mod B. So I fix some A and I want to look at primes congruent to A mod B. It turns out you can modify Euclid's argument for some A's and B's, but not all of them. So if I multiply by so I could look at, say, primes congruent to 1 mod 4 and primes congruent to 3 mod 4. Is every prime either 1 mod 4 or 3 mod 4? Are there any primes that are not 1 or 3 mod 4? Yes. Where is the one prime that's not 1 or 3 mod 4? 2. So every sufficiently large prime is either 1 or 3 mod 4. And by sufficiently large, I mean 3. So except for 2, every prime is either 1 or 3 mod 4. And I could ask, are there infinitely many primes that are 1 mod 4? Are there infinitely many primes that are 3 mod 4? And we could try to look at Euclid's proof. Let's multiply all the primes on our list and add 1 and see, would that work? And so consider, let's say Q1, Q2, dot, 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 Qn, I'll multiply by 4. And actually, I'm going to get rid of the Q1. Where, let's say, Q2, Q3, dot, 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 Qn are all the primes that are 3 mod 4, except for Q1 equals 3. I take all the primes that are 3 mod 4 and I multiply them together. I multiply by 4 and then I add 3. Is this number 3 mod 4? Yeah. Is this number divisible by Q2? No. Q3? No. Is this number divisible by 3? The only way it could be divisible by 3 is if there's no other primes that are 3 mod 4. Is there another prime that's 3 mod 4 other than 3? 7. So we know that this is not divisible by any prime 3 mod 4. So this is 3 mod 4. As Q2 equals 7, it's not divisible by any prime 3 mod 4, and not all prime divisors are 1 mod 4, or else number is 1 mod 4. So we found a new prime 3 mod 4. So if every factor of this was a prime that was 1 mod 4, if you have something that's 1 mod 4 and you multiply by 1 mod 4, you have something that's 1 mod 4. So at least one of the primes that divides this can't be 1 mod 4. So we have to have a new prime divisible by 3 mod 4. So there's infinitely many primes that are 3 mod 4. Extra credit, can you find an elementary way to prove that there are infinitely many primes that are 1 mod 4? If you take 2 primes that are 3 mod 4, what might be true about their product? So give me 2 primes that are 3 mod 4. 7 and 11. Give me something simple. Don't make my math hard. You could do 7 and 7. You could do 7 and 3. We can do 7 and 7. We can do 7 and 11. So 7 and 11 are both 3 mod 4. If you multiply them, you get 77. What is 77 mod 4? You see, that's why you don't give me 7 and 11. It's 1 mod 4. The other way to look at it is if you're 3 mod 4, that's the same as being negative 1 mod 4. So if I multiply two things that are 3 mod 4, I'm just multiplying negative 1 mod 4 times negative 1 mod 4. It's 1 mod 4. So if I give you a number that's 1 mod 4, it's possible that all of the prime factors of it are 3 mod 4. I could have, some problems like that. And so we can't elementary prove that there are infinitely many primes that are congruent to 1 mod 4. Okay, and so what I want to do is I want to talk about how can we use group theory to answer this question. This is one of the strangest ways to answer a simple question I think you'll ever see in your life. I want to prove that if you give me two relatively prime numbers, A and B, that there's at least one prime that's A mod B. Okay, so give me a number. 3. Give me a number that's not a multiple that shares a factor with 3. So I want to prove that there's at least one prime that's 3 mod 7, or that there's one prime that's 7 mod 3. The only way I know how to do this in general, and I think in the last 15 years somebody found another way, the only way I know how to prove that there's at least one is to prove that there's infinitely many. Not only that there are infinitely many, but if you look at all the residue classes, if you fix a modulus, let's say we want to work with 12 hours, how many numbers are relatively prime to 12? So we've done this one a couple of times. So this is like z mod 12 z star. How many numbers are relatively prime to 12? 5, 7, 11, and 1. And they're all their own inverses. So the only way I know how to do this is I show that there's infinitely many primes that are 1 mod 12, 5 mod 12, 7 mod 12, and 11 mod 12. And to first order, the primes split evenly among those. That to first order, 25% are 1 mod 12, 25% are 5 mod 12, and so on and so on. That's the only way I know how to prove that there's at least one prime that's 5 mod 12. I show that the primes fall evenly among all of these groups. It's tremendous overkill, but we developed this machinery that can solve a lot of questions. It solves the original question we asked, but it solves a lot more. It solves not just, is there a prime, but how do the primes split among these different congruence classes? And the way we do this is we use the group theory that you've learned. So what we're going to do is group homomorphisms. And for simplicity, I will assume we have a prime modulus. We'll assume a prime modulus. This is my clock hours. So I will not have a 12-hour clock. What's the closest to a 12-hour clock I would allow? 11 or 13. Yeah. Either one of those would be fine. I can't do 12. I can do things in greater generality. I don't want to spend the time right now. This is not a class in algebraic number theory. I just want to give you a sense of where things go. Let's do a simple case, build some intuition from that. So it's a theorem that if P is prime, then Z mod PZ star is cyclic. And instead of using P, I'm going to use M because we're going to save P for being a prime number. So it turns out that that's a cyclic group. What does it mean to be a cyclic group? It means there is some generated G. So has generator G such that 1 G squared dot G to the M minus 1. So M minus 1 is going to be 1, so this would be M minus 2. Mod M is the same as Z mod MZ star. So we talked about this before. So for example, if M equals 7, 1, 3, what's 3 squared mod 7? 2. And then 3 cubed would be 2 times 3 is 6. 3 to the 4th would be 6 times 3, which is 18. Mod 7, what is 18? 4. And then 4 times 3 is 12, which is the same as 5. And then 5 times 3 is 15. So that would be what would happen if I tried to use 3. 3 would be a generator. So I could take G equals 3. And we saw that we could not take G equals 2. 2 it does not generate. 2 would give us 1, 2, 4, 1, 2, 4. So it's just nice to make things explicit. And then what we're going to do is we're going to define group homomorphisms. So my group is going to be complex numbers of absolute value 1. Or M minus first roots of unity. So if I let U equal e to the 2 pi I over M minus 1, then what would U to the M minus 1 equal? It would just be 1, because that would just be e to the 2 pi I, which is just 1. Is everybody comfortable with e to the 2 pi I is 1? What if I looked at U squared? That'd be e to the 2 pi I times 2 over M minus 1. Then what would U squared to the M minus 1 equal? Also 1, right? I can just switch the M minus 1 and the 2, right? If I wanted to. This would also equal 1. Similarly, U cubed to the M minus 1 would equal 1, and so on. And so what I'm going to do is I'm going to define, chi is going to be a function from Z mod MZ star to the m minus first roots of unity. And I'm going to define it by chi of g is going to be e to the 2 pi I a sub chi over m minus 1 for some a sub chi in 1, 2, dot, 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 m minus 2. Or I want to go up to m minus 2, I want to go up to m minus 1. I'll go up to m minus 1. So I'm defining a group homomorphism, and this becomes a nice way to review what we're doing or what we did this semester. Here's my first group, z mod mz star. Here's my second group, the m minus first roots of unity. Well, you have to show that that's a group under multiplication. Well, that's not too bad. What would the identity element be? It would just be 1. 1 to the m minus 1 is equal to the identity. It's equal to 1. If I take two things such that the m minus first power is 1, and I multiply them, then of course the m minus first power is still going to be 1. Associativity, yeah, complex numbers are associative, so these will still be associative. And then the only thing that is left over is the inverses. Well, if I had 3 over here, the inverse would be m minus 1 minus 3. So it's a nice exercise. All w such that w to the m minus 1 equals 1. It's just prove that that's a group. Are we comfortable that that's a group? And then this is a group. We've played with this a lot. So we have a map between groups. And I claim that this is going to be a group homomorphism. It does still say it's recording. All right, so I think we've recovered. Really hope it does record, because if not, I'm not doing a section 2 today. It does say it's recording. All right, so let's continue. So the goal is to see applications of the group homomorphisms we've been studying. Yes.
Sorry, how do you pronounce that? I've seen it written so many times.
Dirichlet?
Dirichlet.
But that's probably not, it's probably Dirichlet or something like that. If I pronounce it one way, it's almost surely wrong. My favorite mathematician of all time might be Chebyshev, because there's, I think, over 40 different ways of spelling his name in English and transliterating it from the Russian. So almost surely whatever you say is acceptable. I think so. So anyways, do we agree that I just have to specify what it does to a generator? Because everything is a power of the generator. So once it's defined on the generator, it's defined everywhere. And if it's going to be a m minus first root of unity, it has to be of this form. So you give me a choice of integer here, and that uniquely determines the character. That uniquely determines the group homomorphism. So you have to just go through and actually show that it is a group homomorphism. So if I give you, proof chi is a group homomorphism. So if I give you chi of g to the m, I claim that this is going to be chi of g to the m is going to be e to the 2 pi I A sub chi over m minus 1. Oh, I can't use m here. Sorry. Use different. I'll use k. And then that would just be k times that. So this is going to be how I define everything. So if I give you now to the kth power, because I want it to be a group homomorphism, this is how I'm going to define things. And so now if I give you two elements, chi g to the k, g to the l, does this equal chi of g to the k, chi of g to the l? Well, this is just going to be, by the way we're defining things, chi of g to the k plus l, which is going to be e to the 2 pi I k plus l a chi over m minus 1 versus e to the 2 pi I k a chi over m minus 1 and then e to the 2 pi I l a chi over m minus 1. And the way we multiply two exponentials like this is we add the exponents and we see yes. So this is going to be a group homomorphism. So now what we do is we extend to all integers by setting chi of m equal to 0 and then make it periodic with period m. So chi of n is equal to 0 if n is congruent to 0 mod m, and then chi of n mod m otherwise. Well, that's the original. I mean, I could just say it's just chi of n mod m, because I'm now defining chi of m to be 0. So notice that the absolute value is always going to be an m minus first root of unity unless I am a multiple of m, in which case I set it to be 0. So I've got to be a little bit careful here. But I'm taking this function, which is a group homomorphism, I'm extending it. Okay, why do I care about this? It turns out these have a lot of very interesting properties. It's only in the special case for primes, where the modulus is prime, I'm working with a clock with prime hours, but this is actually true in much greater generality. Have you seen the word orthogonality before? Where have you seen that? Linear algebra. So there is a way to kind of generalize this concept. So let's consider all the characters for a given prime modulus m. So for given a character chi, we have an integer a sub chi such that chi of g is e to the 2 pi I a sub chi over m minus 1, and a chi was in 1 to ... m minus 1. So you give me an integer a chi, and that gives me a character. Conversely, you give me a character, there is some a that corresponds to it. There's a one-to-one correspondence. This is a little bit misleading. It's not just nice in general if the modulus is not prime. I'm exploiting a lot of facts because we have one lecture to give you a sense of how group theory arises in algebraic number theory. And so I don't want to do the most general case. I want to do a specific case where I can write things down very concretely and do the calculations. And then if you go into algebraic number theory, to say, actually, we don't really need a lot of this stuff. We don't need the fact that the group is cyclic. We don't need the fact that we have an explicit formula for everything. I'm taking the shortcut today. Okay? If people want to see more details, I'm happy to do optional lectures over reading period or any time in the future and just say, if you're really curious, here's how you do things in greater generality. The following question. what is the sum over all chi mod m of chi of some number n? So I sum over all the values of all the different chi. Do you think the answer depends at all on n? Are there any n where this is easy to calculate? Okay, good. So if n is 0, what would we get? Good. So if n equals 0, we get 0. There's another choice of n that's easy. So think back. You have a group homomorphism. So there's one value where you have to know what it is. What value in Z mod MC star do we know goes to what value in the m minus first roots of unity? 1. So what is chi of 1? So what does chi of 1 have to equal? You take the identity here, where does the identity have to go? But we think back to group homomorphism. Where does the identity have to go to? It has to go to the identity. What's the identity in the m minus first roots of unity? What's the identity element of that group? Of all the complex numbers whose m minus first power equals 1, which is the identity element? 1. So chi of 1 equals 1. Because, chi of 1 is equal to chi of 1. Oops, I want to erase it. Is chi of 1 squared, right? That's one way to look at it. Or 1 equals g to the 0 equals g to the m minus 1. That's another way to look at it. When I'm looking at my group, 3 is my generator. How do I get 1? 1 is either 3 to the 0, or it's 3 to the 7 minus 1, 3 to the 6. So for a group homomorphism, chi of 1 equals 1. That's very important for us. Okay? So now when I'm trying to understand what is the sum of chi of n, if n equals 0, we agree we get 0. What's the next value where we understand what happens? If n equals 1, what would we get? So then you would get 1 every single time. How many characters do we have? Well, the number of characters we have is the same as the number of choices of A. So what would that be? Almost. M minus 1. And it turns out over here, this is phi of m, Euler's Toshin function. This is the number of numbers at most m relatively prime to m. We saw that very early in the semester when we did cryptography, when we did, like applications of Fermat's little theorem. So all of this stuff is coming together. So now, all other n, we get 0. That's nice. So how can we prove that this is? Well, here's one proof. Let's write n as, say, g to the k. So chi of n would be chi of g to the k would be e to the 2 pi I k a sub chi over m minus 1. Do we agree that that's what the effect of chi would be on n? So now the sum over all chi mod m of chi of n, this is basically going to just be the same as the sum of a chi goes from 1 to m minus 1, because you give me a chi, and that's the corresponding value of a chi. So I would have e to the 2 pi I k a sub chi over m minus 1. Can you see the good way to rewrite this quantity? So much about math is pattern recognition. If you look at this the right way, it's trivial. How can I rewrite this exponential? So we saw the harmonic series earlier today. What other series did we see? When we looked at the Riemann zeta function, we saw the harmonic series, and there was another series we saw when we were expanding things. What was that series? Well, the Taylor series was expanding the log of 1 minus x, but when we looked at the geometric series, we had the factor of 1 minus 1 over p to the s inverse. What did we use to expand that? The geometric series. Do you see the geometric series here? How do I rewrite the exponential? So it's the sum a chi goes from 1 to m minus 1. I can write this as e to the 2 pi I k divided by m minus 1 raised to the a sub chi. That's my r. There's a geometric series here. See, they're excited. They're one room away and they're thrilled at seeing this. So this is really the same as the sum. I'm going to switch from a sub chi to L. L goes from 1 to m minus 1 of r to the L. So that's going to be the first term r minus the last term to 1 higher power r to the m over 1 minus r. But r to the m minus 1 is 1, r to the m is r. Or if you want, this is the same as r over 1 minus r times 1 minus r to the m minus 1, but r to the m minus 1 is 1. This is just 0. This shows you the power of this group homomorphism. It allowed me to detect whether or not n is equal to 0, 1 mod m, or something else. Okay, so we can use this to detect a residue. Now consider the sum over all chi mod m of so if I do chi of a, this is going to be 0 if a is congruent to 0 mod m, 1 if a is congruent to 1 mod m, and 0 otherwise. More generally, I could look at the sum chi mod m of chi a chi of b inverse. So let's assume b is invertible. So we'll assume b is invertible. What would we get? So this is going to be the same as the sum of chi mod m of chi AB inverse. What would that sum equal? We just showed above that if I sum over all characters, I get 0 if my input is 0 mod m, 1 if my input is 1 mod m, and 0 otherwise. So what would this sum be? So it's going to be 0 if A, B inverse does not equal 0 or does not equal 1. Right? If A equals 0, we get 0. If A does not equal B mod m, then it's going to be 0. So this is going to be 1 if A is congruent to B mod m. Do we agree? Now, note chi of B inverse is the same as chi of B inverse. It turns out to be the same as the complex conjugate of chi of B. It turns out that this is going to be e to the 2 pi I, whatever the k was for B, times now negative a chi over m minus 1. It's basically just taking the complex conjugate. So really, we could study the sum of chi mod m, chi of A, chi bar of B. And that would be 1 if A is congruent to B mod m and 0 otherwise. What I'm just trying to show here is that we can use these group characters to detect when B is congruent to A mod m. It's okay if you don't understand all the details. This is looking at the forest today, trying to get a sense of what's out there. If you don't understand something completely, that's fine. If you don't understand something at all, let me know right now. All I want you at this point is to see that I understand when I sum over all the characters, I get 0 if n is 0. Oops, sorry. I get 0 if n is 0. I get 1 if the input is 1. Oh, so I get n minus 1 if the input is 1. And for all other n, I get 0 because of the geometric series formula. This proof doesn't work in general. You need more work. I don't care. But this detects whether or not my input is 1. Okay, well, instead of detecting if my input is 1, could I detect if my input is 2 or 3 or 4? Yes! I just do a simple shift. And so I now just put this factor of chi of B inverse. And now, if A is congruent to B, I get m minus 1. Otherwise, I get 0. Oops. It shouldn't be 1. It should be m minus 1. Often in these sums, they divide by m minus 1 so that the sum is 1. This is what the orthogonality is kind of meaning. It detects if it's 1 or not 1. And so now we can use this to prove that there are infinitely many primes in arithmetic progression. As a nice exercise, and I debated putting this on the exam, prove Taylor-Seward's theorem that there are infinitely many composites in arithmetic progression. So if I give you two numbers a and b, they don't even have to be relatively prime, prove that there are infinitely many composite numbers congruent to a mod b. That's a nice exercise. See if you can prove that. So show infinitely many composites congruent to a mod b. We want to show Dirichlet's theorem. So Dirichlet, if A and M, oops, I'll do mod M. If A and M are relatively prime, show infinitely many primes congruent to A mod M. And here's going to be a sketch of proof. And let's assume M is prime. Okay, so I'm going to sketch the proof as to what goes on. So we have the zeta function is the sum of 1 over n to the s. And it turns out that this is the same as the product of 1 minus 1 over p to the s inverse, at least if the real part of s is greater than 1. Ls chi, I'll define as the sum of chi of n over n to the s is the product of 1 minus chi of n, p over p to the s inverse. So you just have to show that this sum is the same as that product. And so rather than doing 1 over n to the s, I'm doing chi of n, where these chi's are what we defined a moment ago. If I look at the log of Ls chi, this is going to be the log of the sum of chi n over n to the s. It's going to be a sum over primes of the log of that. Well, the log, I'm going to get a negative sign coming out. I'm going to Taylor expand as before. I'll get chi of p over p to the s plus something good. And we're going to ignore this. Okay, so is everybody comfortable that the main term is going to be chi of p over p to the s, and then we'll have good stuff? This is just exactly what we did for the Riemann zeta function. We just expanded out. Okay, now here's where things get beautiful. Let's look at the log of Ls chi times chi of A. That's going to be the sum over primes of chi of p, chi of A over p to the s plus good s chi of A. And so rather than doing an A, I'm going to do A inverse. Okay. Why do you think I'm doing an A inverse? Yes, we can then use what we just had a moment ago. And now if we look at the sum over all chi mod m of the log of L s chi, and I'll put the chi A inverse in front, doesn't really matter. This is going to be the sum over all the primes. I'm going to just switch the orders. And yes, I warned earlier today that you have to be careful about switching orders. That was a long time ago. I'm going to forget about that now. P to the s. And I'll have the sum over all chi mod m of chi of p A inverse plus something good. This is going to be m minus 1 if p is congruent to A mod m and 0 otherwise. So all we have to do is, if this side is infinite, then we have infinitely many primes congruent to A mod m. So we just have to understand these functions here. It turns out one of these functions is the zeta function, which blows up. And then all of the chi, except for one of them, it's easy to show gives a finite value. There's one of them that's difficult and tricky. That's where the meat of the proof is. So you have to do some work. But in one class, we proved the matrix conversion, and we gave a sense of how these group homomorphisms actually matter and arise in number theory. This allows us, this is a proof sketch of this infinitely many primes congruent to A mod m, again, tailored with a different spelling than the tail from before, tailored to the fact that I'm using m as a prime and taking into account all of that stuff. But all we have to do now is some number theory on this side being infinite. All right, so this is a good place to stop. If you have any questions, just let me know.